Yeah, now is good.
So now you can see me.
Yes, now it's good.
And I will pin this video. Everything is being recorded. Good. All right. So Patricia trees, they were these trees in which each node stores an array, which is as long as the alphabet. Each edge stores a string on it that starts with the corresponding letter of the alphabet. And this represents a set of strings. And what set of strings does it represent? Well, it's the set of strings that you get if you follow every possible path from the root to a node and concatenate the strings that you see along the way. And one of the tricks about this thing, which was nice, is we're supposed to think of it, although we imagine that the labels are attached to the edges, what's actually happening is off to the side, there is a collection of strings, like maybe this one, and this one, and in fact, these labels, they're just represented as pointers into these strings along with a integer length. So this one is pointing to here, and then this one would be pointing, for instance, to here. Okay. So it's good to think of the tree as being something separate from the storage for the labels. And the reason for doing that is, well, you can use this to store a set of strings, and you can search in it and check if something is in the set and find the things that are close to it and the things that start with the same sequence as the things that you're searching for. So lots of things like that. But what it's really useful for is the following. You take one really big string and I mean really, really, really big, and you make a Patricia trie that stores not just this string, but every suffix of this string. So it stores this string, a string that is long. It also stores the one that starts with the first space and goes all the way to the end. It stores the one that starts with the S and goes all the way to the end, and so on. And if you do that, so if this is a string of length n, then you get a Patricia trie with n leaves. And every internal node, so every node which is not a leaf, has at least 2 children, which means that you get less than n internal nodes. So you get this structure over here, which is of size n, and all of the labels on the edges, even though they can be quite long, they're all represented just by pointers into this one string here. All right. Now, why is this a useful thing to do? Well, this is a useful thing to do because it lets you search for any occurrence of any string inside this string. So, for example, if I want to know if hat is inside this string, well, there is a suffix that begins with hat, and therefore there's going to be a path in here that starts with H, and well, there'll be a path that matches the full way to hat. Okay, so that all seems sort of easy and obvious, but if you think about it for a bit, it's actually incredibly powerful. How long does it take me to search for hat? Well, I start at the root, I look in an array index, and I check 3 characters. So the amount of time that it takes me to search for this string like this is just proportional to the length of this string. And that has nothing to do with the length of the string that's stored in here. So in particular, the string that's stored in here could be the concatenation of every book that was ever written by anybody in any language. So huge, huge thing. And if I want to know, did somebody ever use this particular phrase before, some sentence? Well, this can check it in time that's just proportional to the length of the thing I'm searching for. Okay. So it's a really powerful thing. So take all of every web page on the internet, all the text that's in those, concatenate them, stick them in a suffix tree, and enter whatever phrase you're looking for. Well, the suffix tree will tell you whether or not that thing occurs. And if you want, it'll even, from that, you can read off one of the locations where it occurs. And if you're willing to traverse to the leaves of it, you can actually read off every location that it occurs. Okay. So this seems like an incredibly powerful thing. And the space is, well, this tree has less than 2n nodes and leaves and internal nodes. The internal nodes store arrays, and those arrays have length that's proportional to the length of the alphabet. So that's n times sigma. And then there's the one string off to the side, which stores all of the stuff that you, all the data that you have there. But that's just of length n, so that doesn't add anything. Okay, so you get pretty good storage and searches that have nothing to do with how much data you have, but just have to do with how long the thing is that you're searching for. All right, that's all great. Good space, fast search time. What else would we want from a structure like this? Add and remove, sure. But even before that.
The size?
Well, the size is good, pretty good. So it's linear times the size of the alphabet. But there's one thing that would prevent me right now, from what I've told you, from using this as is to store even every work that Shakespeare ever wrote. And that would be building it. So even though it has linear size, the only thing that we've seen for building these Patricia trees is, well, you insert the strings that you want to, we know we can add and remove strings from Patricia trees, but in this case, the strings that we want to add, well, there's n of them, and they have lengths n, n-1, n-2, n-3, and so on. And if the string is particularly repetitive, then the time, then basically the time it takes to add these things will be quadratic, n squared. So in particular, if the string looks like this, it's extremely boring. Then the first thing I do is insert the whole string, and the next thing I do is insert the string starting from the second position. But in order to do that, I have to search for that string, and the search proceeds all the way right up until the second last character before it sort of falls off the end. In fact, the last character before it falls off. So that takes, the first one was quick, the second one takes n-1 steps, then the third one is going to do the same thing. It's going to take n-2 steps and so on. And eventually it's going to build, well, maybe I should draw it this way. It's going to build a Patricia tree that looks like this. There'll be a path where every edge is labeled with an A, and hanging off each of those will be an edge with the end of string character. And the way we've built that is by basically by traversing this path n times. So what would be nice is if we could construct this thing efficiently. Otherwise, it's kind of hopeless, or it's not hopeless, but it's we love this thing because it can search in time that's independent of its size, but we do need to be able to construct it in some reasonable amount of time. And if its size is in the billions, well, a billion squared is not a reasonable amount of time. Yeah. Well, so the first time we insert, it happens very quickly, and it looks like this. So we started basically this node. There is no child labeled A, so we're done. The second time, we're going to be searching for this string, but there's one less A than here. And the way that that works is, okay, we see there is a child, an edge coming out that starts with an A label. So we have to start matching these characters to see the first time that they differ. So we scan the whole thing and then realize, this one has the end of string character just before the end of this one. And that's the thing that creates this node. Yeah, so you get the idea. So then you get a whole bunch of A's up here, an $A here, and a $1 here. And that's gonna keep happening. Okay. All right. So let's keep in mind we have this nice suffix tree. It's called great data structure, but we don't know how to build one efficiently yet. So we'll eventually get to a linear time algorithm for building this thing. But before that, we're going to look at something that's interesting on its own. It's called the suffix-array. But not only is it interesting on its own and useful for a lot of things, but it is it's in order to build a suffix tree, it's a lot easier if you're given a suffix array first. So we'll do this in a few steps. So we'll come back to these suffix trees and how to build them efficiently, but first, suffix arrays. So what is a suffix array? I had a demonstration that all of you could watch. Not a demonstration, but some prepared stuff that all of you could watch. Now I'm not sure how I'm going to deal with it, but we'll see. Okay, so those of you at home should see some picture there.
Yes, we do see.
All right, and those of you here can see this picture too. Okay, so what's a suffix array? Well, if you think about the suffix tree, I mean, it stores all the suffixes of some big string. And from the tree, if you read the leaves off left to right, you get the suffixes in sorted order. So with the ones that start with A first, and then the ones that start with B, and so on. So a suffix array gets that part of the structure the same way. So here's an example. So the string that I'm considering here is too many apples. So it's the thing marked with an S near the top of the picture. There's no spaces because spaces are hard to show you. So there's no spaces between things. Yeah, so the string S with too many apples, and it ends with this end of string character, this $sign. And what the suffix array does is it takes all the suffixes, or the way you can imagine it is you take all of the n suffixes, you sort them, and then the suffix array tells you what that sorted order is. And the way it does it is the first element in the suffix array, so element 0 in the suffix array, is the index where the first string in sorted order starts. So in sorted order, the first string is the empty string, the one that ends, that begins with the end of string character. So that empty string is at position 13 in the string. So the first integer in the suffix array is the integer 13. It says if you want the lexicographically smallest suffix, it starts at position 13. Now the next string in sorted order is one of the ones that starts with an A. It's any apples. That A starts at position 4 in the string, so the second element of the suffix array is a 4. Okay. And in fact, the way that this list of strings that you see here is generated is just by going through the suffix array and and printing the suffix that begins there. At least that's what the black part is. And I've also put a second red part there, which is just what you get if you wrap around the end of the string and continue until you get the full n characters. And why did I do that? Well, I did that because we've seen that picture before. That picture came up when we talked about the Burroughs-Wheeler transform. So the thing that's really useful for data compression. And what was the Burroughs-Wheeler transform of a string? Well, it's actually the last column in that picture. So the Burroughs-Wheeler transform of a string is you do exactly this. You sort all the suffixes with the wraparound so that they all have the same length. So the first column then gives them to you in sorted order, and the last column is the Burroughs-Wheeler transform. And so if you have a suffix array, you get the Burroughs-Wheeler transform for free, right? How does that happen? Well, you just take whatever, right? So the suffix array at the first thing in the suffix array is 13, meaning it's the last element of the string. And so what's the first thing in the Burroughs-Wheeler transform? It's the element that came before that, the element at position 12. And the second thing in this thing is 4. So what's the second thing in the Burrows-Wheeler transform? It's the thing that came before that. It's the element at position 3. That's the M. Okay. So you can read this off directly from the suffix array. Yep. No, the string at position 4, so it's annoying that I can't point to two things at once, but at position 4 in this string starts there, any apples. Right, that's index 4 in the string. Yes, it gets confusing. Right, so this is, think of this as the index in the suffix array, or the, well, this is the list of strings in sorted order, but it also tells you what's happening inside the suffix array. Like the suffix array, the first thing in the suffix array at position 0 is pointing you to the last character of the string. This one is pointing you to the 4th character of the string. This one's pointing you to the, what is that, the 7th character. That's this guy over here, apples, and so on. Okay. Okay. So there's another useful thing you get from the suffix array. You get the Burrows-Wheeler transform immediately if you can compute the suffix array. All right. So even if we didn't care about suffix trees, it seems like this suffix array is useful, well, because we know it's really helpful for data compression. And we would like to know how to compute it quickly. Well, there's some obvious things we can do. Well, we know how to sort things. And we know some fast sorting algorithms, n log n times sorting algorithms. So we could use one of those. The problem if we just try and use one of those is going to be the same thing that happens, the same problem with trying to just insert things into a suffix tree. So, right, we know these n log n times sorting algorithms. But these sorting algorithms are comparison-based. In fact, they do n log n comparisons between elements. So the running time is n log n, provided that you can compare two things in constant time. But that's not necessarily true for suffixes of strings. Again, if you give me two strings that both start with the same prefix, then I can't compare them quickly. I mean, I have to start comparing them from the beginning until I see the first difference. And exactly the same problematic string that's bad for suffix arrays, the one which is just all A's, is going to cause the same problem here. Because, yeah, this does n log n comparisons, but somehow typically you're going to always be comparing two things that are, you have to look at n over 2 values before you find the difference between them. So this n log n comparison algorithm becomes n squared log n time. That's terrible. Then you might as well actually use a way to build the suffix array would be to just build the suffix tree, because there at least you don't get the log n. So that would be, so this is not helpful. So we're going to try and do better, and we're going to give an algorithm that builds one of these things in O of n time. So this is an algorithm that has a short input.
Sorry, but the board cannot be seen.
Yeah, I'll stop.
Can you remove the program?
I'll stop sharing this screen now.
Thank you.
Okay. So we're going to see how to build this thing in linear time. Okay, but first, a couple of things to remember. Let's remember counting sort and radix sort. So does anybody remember counting sort? Anybody seen that before? So what does it let you do? So it's a sorting algorithm. Yeah. Yeah, it has two arrays. Okay, and one of them is the counting array. But what does it need? What kind of data does it need to, I mean, what kind of data can it sort? Integers, yeah, small integers. So in particular, with counting sort, you can sort n integers in the set, let's say 0 to n minus 1 in O of n time. So maybe there's duplicates or not, so not every element occurs exactly once, but counting sort lets you sort them in O of n time. And it's a really simple thing. It uses the integers as indices into arrays, and it uses a second array to just count. How many times does 0 occur? How many times does 1 occur? How many times does 2 occur? And then using that, it can take your input and shove everything in the right place. That's kind of easy. What's cool about it is it can be used as a subroutine into radix sort to sort larger sets of integers in the same amount of time. So can sort integers and integers in the set 0 up to n to the c minus 1 for, let's say, some constant c, and O of c times n time. Okay. And the way to think of it is the integers in this set, they're sort of like just c tuples, where each element of the c tuple is an integer in the range 0 to n minus 1. And the way radix sort works is by running counting sort, looking only at the lowest order bits first, followed by the next. Once that's done, it does the same thing again, looking at the next highest order bits, and then finally finishes with the highest order bits. Remarkably, that works because counting sort happens to be stable. Not important that you understand all that. Just know that you can sort these kinds of small integers, where small means polynomial in n, basically in linear time, as long as the degree of that polynomial isn't big. And for us, we'll use, like, c is going to be 2 or something. So 2 passes of counting sort. All right, that's one thing to remember. Another thing we need to know is this recurrence. And so if I have an algorithm that does a linear amount of work and recurses on a 1 subproblem of size 2n over 3, then that algorithm runs in linear time. And that's really easy to see just by expanding this out. You see you get a sum that has a 1 times n, and a 2/3 times n, and a 4/9 times n, and so on. It's a geometric sum. The whole thing only adds up to 3 times n. but this is the recurrence that we're going to get. So this is going to be a recursive algorithm with this recurrence. All right, and I will share my screen once more because there's the sort of third thing we should keep in mind, and that is that sorting is the same as ranking. So on this thing that you see at home and this thing here, there's a sort of third list, which is about, it's marked with rank. And you can read it off. It tells you, so the rank of an element is where it fits in sorted order. And so, for instance, the rank of the suffix that starts at position 0 is 12. So what is the suffix that starts at position 0? Well, it's the suffix too many apples, and it's second last when we sort things in order. Okay. So it's basically, well, it's exactly the inverse of the suffix array. So so if you, in fact, it's the inverse permutation. The point that I want to take from this, without having to talk about it too much, is that sorting and ranking is the same problem. So the suffix array is a permutation that you can use to print out or get the suffixes in their sorted order. The rank array you can get from the suffix array with a simple scan. So what that does, what that tells you is for each suffix, what position is it at in the sorted order? Okay. Right, and so you can see in this example, the element of rank 12 is 0, and so that shows up in the suffix array with at position 12 is a 0, and that shows up in the rank array at position 0 is a 12. And that's the same for all the other things. Okay, good. So now the input is a string of length n over the alphabet zero up to n minus 1. Okay. So this is pretty generous. It feels generous. Usually we think of strings, in particular, if we're talking about really long strings, they're quite long and the alphabet is small, like 26-letter alphabet and a string of length 1 billion or something. But this algorithm can handle any string as long as the size of the alphabet is not more than the length of the string. And in fact, if you think about it for a little bit, you'll realize that by this radix sorting, that means it could even handle bigger alphabets. I could put a C here, because if I'm only using n characters of this big alphabet of size n to the C, I can first sort the characters that appear, equivalently get the ranks of those characters, which means then I can replace each character by its rank, and that will, of course, be a number between 0 and n minus 1. Since there's only, the string only has length n, there's no character that can have rank bigger than n minus 1. Okay. Good. So that's sort of the first application of this relation between sorting and ranking. We'll use that a couple of times. So this is the string we've been looking at. So I'm going to say let S0 be all the suffixes you get that have this form, Si up to Sn, where I is congruent to 0 mod 3. So 2/3 is going to show up here somewhere, so 3 is going to show up somewhere. So we're going to have this set S0, which is all the suffixes of this string that start at indices which are congruent to 0 mod 3. So what's in S0? This is in S0. This starts at position 0. This is in S0. It starts at position 3. This is in S0. It starts at position 6. This is in S0. It starts at position 9. And 1, 2, 3. This is also in S0. And when I say this is in S0, I mean the suffix that starts here is in S0. And the suffix that starts here. So the suffixes are too many apples, e apples, and plus. And just S. Okay. And S1, actually not S1, we'll call it S12. Okay. Then there's the other suffixes.
Yeah, Pat, I have a small question.
Yes?
Is there any reason why we choose mod 3? Like, is it because of the recursive formula that you've shown?
We will see why 3 is somehow magical here. And so I'll just say this is an algorithm due to Sanders and Karkinen. So it's not the first linear time suffix array construction algorithms. In fact, suffix arrays are so important that there's been a whole sequence of algorithms for constructing them. But prior to this one, there was a similar algorithm that didn't break the string up this way. It broke it up into even and odd characters, or even and odd indices, so just mod 2. And it turns out, surprisingly, that actually, and this people didn't notice for years, it actually turns out to make things much easier later on if you do mod 3 instead. We'll see where that happens. There'll be a sort of light bulb moment where you realize that was the right thing to do. Okay, so here's the algorithm. A, recursively sort the set of suffixes S12. Sort the set of suffixes S0. So it's a merge, so it's going to be a merge sort algorithm. So we sort one part of the input. We sort another part of the input. This happens to be 2/3 of the input. The other part happens to be 1/3. And then we merge I mean, that's it. You merge those two sorted sets, two sorted lists, let's say, to get the final sorted order of all the suffixes. And notice that I somehow was a little, I used different wording here, and that's because we're going to, step A is going to be done recursively, step B is actually going to be done using radix sort. So let's start with step B, because it's actually the easiest. So how do I sort S0 easily using radix sort? Well, let's look at a string, and I get to do this after I have already sorted S12. We have to do these in this order. Okay. So if I look at a string in S0, for instance, here's a string in S0. It starts here and goes on. What is that string? That string is a one character, M, followed by a string in S1, or if you like, a string in S12, right? So it's one character, and then after that character comes a string that's in S12. All right? So this character here, by assumption, is an integer in the set 0 to n minus 1. But all our characters are in that set. This string in S12, it's a big string. But I've already sorted all of the strings in S12. And sorting and ranking are the same thing. So that means that I know the rank of this string in S12. What's the rank of this string? It's just an integer that tells me where it fits in the sorted order of S12. So that is actually another integer in the set. This time it's only 0 up to 2n over 3 minus 1. Okay. So if I wanted to compare two strings in S0, well, I can start by comparing their first characters. If they're different, I already know. And if they're the same, then I can compare their second parts. But their second parts are just two integers now. Because I mean, they're two different integers, so that will resolve the comparison. So that means that I could use something like quicksort or whatever on that. But even better, the two parts of this thing are just two integers, which means I can use radix sort to sort them in linear time. Okay. So once I have already sorted S12, then sorting S0 is easy, because everything in S0 is, you just think of it as a two-part thing. First character, and then whatever's next. Okay. Is that clear? Good. All right. Let's go to step A now. Recursively sorting S12. So the way I'm going to do that is the following way. I'm going to write this string twice. Starting from position 1. So the first time I'll start from index 1 here, which is the second character of the string. And I'm going to group things into 3 letter groups. And then when I get to the end, I will pad it with $signs to make sure that that last group is full. So it's a nice multiple of 3. And now I'm going to write the string again, but starting from the third character. So the one that starts at index 2. And I'll do the same thing. Break that up into groups, 3-character groups. And pad that out with the end of string character to fill out the last group. All right. Good. So let's think about what's happening here. So why did I draw these blocks? Well, if I look at what I have here, in particular, if I look only at the strings that you can make by taking full blocks, so not starting in the middle of the block, then I see the first one contains all the strings that start at indices that are congruent to 1 mod 3, right? It's this one, it's this one, it's this one, it's this one. All of those strings I can make just by taking full blocks. And over here, in the second part, well, I can make any of the strings that start at positions 2 mod 3 using only full blocks. And it might seem weird that I've somehow mixed these up, but actually the fact that I separate them with this end of string character here means that if I try and resolve, if I do some comparison between 2 strings, it will get resolved. I mean, so if I try and compare some string that starts over here with some string that starts over here, I will know the answer without having to have this string walk into the second part. So, so this actually, if I was only to think about the things that use full blocks here, I actually have every suffix in S12 available. So every suffix of this contains every suffix of that's in S12. And yes, some of these suffixes are longer, but it's not going to matter for the purposes of sorting because any comparison that I want to do with one of those longer ones will be resolved before I go into the second part. All right, so now I've got these blocks. What's one of these blocks? This is an integer, this is an integer, and this is an integer. So that's a triple of integers in the range 0 to n. Or another way to interpret it is it's an integer in the range 0 to n cubed. Right. 3 integers in the range 0 to n minus 1, I can treat like 1 integer in the range 0 to n cubed. And so just the blocks by themselves, don't think about the suffixes now, just the blocks, I can sort those using radix sort. So that is radix sort with c equals 3. So that runs in O of 3 times n time, which is O of n time. Okay, so I could sort the blocks. It's not what I want. What I want is the suffixes sorted, but I can definitely sort the blocks. But remember, sorting and ranking is the same problem. So once I've sorted the blocks, I can also get the ranks of the blocks. And now I can replace each block by its rank. Well, how many blocks are there? I wrote the string twice, and each block is of size 3. So the number of blocks is only 2n over 3. And therefore, the rank of any block is at most 2n over 3. So these ranks come from the set 0 up to 2n over 3. Okay. So if I write out now the ranks instead of the contents of the blocks themselves, I get something that's exactly the same in terms of sorting. Right? So you see, for instance, that, well, out of all of these blocks, which one is going to have the smallest rank? It's going to be one of the ones that starts with an A. It's going to be this one. And actually, the other one, the next one, is going to be this one. But the point is, if I wanted to compare these two blocks, then I could do it by comparing the letters one at a time, but I don't need to now. I just compare those two integers. So the result will be the same. So I just took this string and turned it into a string whose length is 2n over 3, and the alphabet is also in set 0 to 2n over 3. That's the kind of input that I can sort recursively. The size of the alphabet is no more than the length of the string. I can sort it recursively. So that's how that goes, right? So if we're looking at the running time, we're shooting for this recurrence. What have I done? Yeah, there was a recursion on something of size 2n over 3. And so far, I've only done O of n work besides the recursive work. And that work was, well, to do the sorting and ranking of these blocks and to build this string and so on. And then again, to sort S0 using radix sort with this neat trick that I could use the ranks of the resulting strings to do that. So now all I have to do is figure out how to merge S0 and S12. That sounds easy, you say. I mean, I have two sorted lists now. Merging two sorted lists, that's sort of an algorithm you learn sometimes in your first programming course. Certainly by the time you've taken an algorithms course, you've seen merge sort, which the main step of merge sort is to merge two sorted things. Right? And you've seen it. It's basically you keep two pointers, one into one list, one into the other. You compare these two things, and then you decide whichever is one of them is smaller is going to be the next thing that goes in your sorted list, and then you move along to the next one. Repeat. And that's the same algorithm we're going to use here. Nothing special. That's a good algorithm. It runs in linear time. We just have to make sure we can take two elements and compare them. Because one of these blocks consists of strings that come out of S0, and the other one consists of strings that come out of S12. And, well, it's not obvious that we can compare those things in constant time. I mean, we can certainly compare them by scanning their characters until we find a difference, but that's not what we want. We want constant time comparisons. Well, let's make sure we can do that. So I'll always have some string from S0, and I'm comparing it to a string in S12. Now, that second string could be from S1 or it could be from S2, meaning it could be starting at a position that's congruent to 1 mod 3 or a position that's congruent to 2 mod 3. Okay. So let's consider the first case where it starts, where it's a string in S1. Okay. All right, so a string in S0, we already saw this. It consists of one character followed by a string in, well, it's actually a string in S1, which is also a string in S12, because S12 contains S1. This string, so I could compare this string directly to this string, but that's no good. That's not what I need. Luckily, this string is some character followed by a string in S2, but every string in S2 is also a string in S12. So in order to compare a string from S0 and a string from S1, I compare their first characters, and following those things is a string from this set S12, and this is also a string from the set S12. I already know the rank of this string, and I know the rank of this string, so I only need to compare those two ranks. So it's just comparing two integers. So that resolves the comparison if I need to compare something from S0 with something from S1. Well, the only other possibility is I need to compare something from S0 with something from S2. Well, we can try the same thing. S0 starts with some character followed by a string in S12. S2 starts with some character followed by a string in S0. That's no good. I can't compare strings in S12 with strings in S0. In fact, that's what I'm trying to do. So what do? This is the light bulb moment.
I think we can take two elements out of S0.
Instead of immediately trying to do this by comparing with the suffixes, let's just go one character deeper. S0 is two characters followed by a string in S2, right? This is the index congruent to 0. This is congruent to 1. Here, this is starting at congruent to 2. So that's in S2, which means it's in S12. This string, this is congruent to 0. This is congruent to 2. Second character is congruent to 0. Third character is congruent to 1. So a string in S1 is also in S12. So to resolve the comparison between these two types of strings, one in S0, one in S2, I compare the first characters, I compare the second characters, and then I know the ranks of what comes after that. So 3 comparisons. So that's why 3 is the magic number here. If you do this with 2, you get this annoying flip-flopping situation that there's no easy way to compare something from S0 and S1, because something from S0 is a character followed by something from S1, and something from S1 is a character followed by something from S0, which is hopeless. But when you do it this way, you resolve any comparison after looking at most 2 characters and then the rank of something. Okay. So then the merge requires only a linear number of comparisons and otherwise linear time, and each comparison takes constant time. So you finish this in linear time. It's a beautiful algorithm. It's sort of the product of, like a decade and a half at least of people building suffix arrays and coming up with different algorithms for them. This is probably one of the most elegant of the bunch. And then, of course, after this, some people did some further algorithms engineering work to make it faster, but a little bit uglier. So, and you can read the paper. In fact, the appendix of the paper has 50 lines of C++ code that does this. Questions? So, and of course, as I said, this gives you the suffix array. From the suffix array, you can easily read off the Burroughs-Wheeler transform, which was somehow this magic thing that we saw. Now you know how to make it. Okay. All right. So we can compute the suffix array in linear time. Now, we will see that the suffix array just by itself, well, with a little bit of extra information, is actually a pretty good data structure for searching for substrings anyway. But we were talking about suffix trees and thinking that maybe we can get well, we can use the suffix array to speed up the construction of a suffix tree. And yes, we'll do that. And I'll just tell you one more thing. So there's a thing called the longest common prefix array. Okay, so that thing, we'll see how to compute it next class in linear time. It's actually fairly quick to get from the suffix array, but it's a little confusing to get your head around what's happening. But what it tells you is the length of the longest common prefix between S suffix array at I and S suffix array at I plus 1. I'm sorry, up to Sn, and this one also up to Sn. Okay, what does that mean? Well, the way to think of it is the suffix array represents what happens when you sort all the suffixes in some order. And when you do that, what tends to happen is, you get things like apple shows up beside, next comes something like apply. And what the longest common, so this will be at, let's say, position I in sorted order. This will be at position I+1 in sorted order. The LCP array at position I will tell you the number 4 because these two things in sorted order, they agree in their first 4 characters. Seems like useful information to have. It means if you wanted to compare them now, you'd start further down. I mean, you'd start at character 5. Okay. All right. So for now, let's say we have that thing. So we have the suffix array. We saw how to construct that in linear time. We will see how to compute the longest common prefix array in linear time. For now, let's say we know how to do that. How can we use that to make our Patricia tree? Well, now we can actually run the algorithm we were sort of thinking of, which is you take the suffixes and you insert them into the Patricia tree in sorted order. Okay, so we do that. And well, for our example, what was our string again? Too many apples. So the first string in sorted order is just the empty string. And what we're going to do is something that showed up in assignment 1. We're constructing a search tree given the elements now in sorted order. So let's just keep a pointer to the last leaf that we created, which actually represents the largest element that's currently in the search tree. So we do that, and that's going to be somehow the place that we start from. So, right, so then the next thing in our sorted order is any apples. So the next string we want to insert is any apples. So that would be the suffix array at position 1 is the thing that says any apples. And we have this longest common prefix array, which tells us what's common between this string, the one we just inserted, and the string any apples. In this case, the longest common prefix is of length 0. This is the empty string. The other one is the string that starts with an A. So we know the length of the string that we are currently inserting, any apples. We know that because basically this is just an index into an array of length n. We know that the length of the string is n minus that index. And we know the longest common prefix between the string we just inserted and our string. So what we can do is, so it's boring here because we're going to walk back up one step and know immediately. So we know immediately to start at the root. But the general picture is we just finished inserting something. There's a whole bunch of tree we already built here. Here we are. We know the length of this string, everything else. And we're about to insert a new thing. And we know how much of this new thing, what the length of the common prefix is between the new thing and our current string. So that actually tells us, because we know the length of this string, we can look at the label on this edge and see, well, do we need to go all the way back up here? Because so if I trim off this much from this string, do I get into the common part or not? So, you know, whatever this string is, you've got it. These labels here break it up into chunks, and I know that the string I'm about to insert matches it up to some length like this. And so I just break off these chunks until I get to a chunk where I can't break it off without running into the common part. And what that corresponds to is walking back up this path in the tree, right? Because these chunks are the labels on these edges here. And then finally I get to this edge, which corresponds to this chunk here where these things differ. where they agree for a while and then differ. And that's the place that I will need to insert a new node. And then I can finish the insertion by putting whatever the rest of this strings label is onto there. Okay. So how long does that take? And then my next search is going to start from here. So how long does that take? Well, it's hard to say because I walk up. I mean, I could have to walk up a long way here. So it could take a long time, it could take a short time. But here's the important thing. At any point in time, there's a path from the root of my suffix tree to the largest value. That path has some length. When I run this step, the length of that path decreases by as much as I had to walk up. And then it increases by 1 for the new thing that I just added. Maybe 2, it doesn't matter, 1 or 2. That's not important. So if you think about that for a while, that means that the total time I spend walking up these things is not more than 2 times the number of strings in my set, right? Because all that happens at each step is I delete, 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 and then I add 1 or 2. And I can never delete more than I have. So the total time that I spent walking up here is not more than the number of things I added, which is not more than 2n. 1 for the split node and 1 for the leaf. Okay. So with the suffix array and the LCP array, you can build a suffix tree in linear time. All right. So that's a good place to stop today. Questions? Yep.
So basically, we save time by sorting the data first.
Yeah. Yeah, you save a lot of time by sorting first. Then you can build this thing. The algorithm for repeated insertions, as long as you keep a pointer to this this last thing that you inserted, you're good. Now, if you may have missed it, what did I need the longest common prefix thing for? Well, I needed that to know how far up I need to walk without having to look at the whole label that's on each of these edges. Right? I just need to know the length of the label on each of these edges. I don't need to look at it and compare it to anything. That's where the longest common prefix is needed. So the time it takes me to walk up is not the length of the string that I'm deleting, but rather just the number of nodes in the tree. Okay. Other questions? Okay. All right, thanks.